Remember I was talking about how the sun being a black hole, the earth and all this stuff, the center of galaxies, and why, things don't fall in. In fact, I'm in the middle of writing a paper. I've been writing it for like 4 years, on cosmology, where I'm describing all this. I'm describing universal evolution in terms of black hole theory, but as well showing that, matter production occurs at the surface of black hole, meaning that matter didn't just appear in some miracle called the Big Bang in standard physics, right? Really, the Big Bang theory is really not scientific. It just banged, and boom, here we are. You might as well go to church and be told, yeah, God did it, right? It's about the same. So it's not just a black hole gathering matter around it, but it's a black hole producing matter, from the middle. And that would be why planets expand. And that's a whole other thing that's even more heretic. I independently, and then find out that somebody else had done it before me, I independently, in my little van, realized that if this is all true, then at the center of the earth there must be a black hole, so then there must be matter production, so that means that they would produce pressure on the surface of the earth, and that the earth would have to expand throughout time. And then I at the time did the best I could with modeling, trying to figure out if I took the earth and shrunk it down, would all the continents fit together? And then I found yes, it's actually a perfect fit, much better than plate tectonic ideas where as if the earth was flat, like a map, and so you can shrink the planet by about 60% and all the continents fit together perfectly. And you can do the same with the moon. You can do the same with some of the moons of Jupiter and so on. It's been done. So if you look up on YouTube, somebody did a nice animation of it. If you look up Earth expanding, it should come up. There's nice animations of it. So clearly, what I was saying is that basically the universe is making singularities, and matter organizes around it, so that you can think of it like our sun. But on the sun there's some evidence, for instance, that are being ignored. There's huge black spots on our sun. They're called sunspots. And when I first started, I was told, at the time, the idea was that sunspots were just surface event, just optical illusion, basically. But I was saying, no, they're actually holes that matter is being sucked into the singularity in the middle. And since then, they discovered, yes, they can see the material being sucked in the middle of these so-called sunspots, which are huge vortices in the plasma of the black hole, and the vortices are huge, right? They're 13 times the size of the Earth, and from it, the hottest X-ray on the sun comes from those holes, right? They emit massive amount of X-ray, which is exactly what's predicted when matter falls into a black hole. Okay, so sunspots, but so I start to think, okay, well, must be true that not only the sun, but our galaxy and so on, but as well atoms must be centered by singularity, right? And so I start to do some calculations to see if there was any evidence of that. And there is, but it's as a result of some, historical manipulation of mathematics, it was missed. And so I tried to explain it in this paper called the Schwarzschild proton paper. So, you know, I tried to be subtle. I was going to call it the black hole proton, but then it was like, I knew I was going to get bricks thrown at me, so I tried to soften it by calling it the Schwarzschild proton paper, because the Schwarzschild solution is the solution to a black hole. I figure people would get it, right? And I calculated it. I calculated, okay, what would happen if I made the little proton a little black hole, right? And so to do that, you know, the proton mass is not high enough to be called a black hole. So I said, well, yeah, but what about all the vacuum energy that's inside the volume of a proton? What about all the energy that's there that's being ignored? So I calculated the volume of a proton, right, which is very teeny, 10 to the minus 39 centimeter cube, right? And I calculated how many of the little Plancks fit in there. And it turns out that the mass of all the Plancks that fit inside one proton is the mass of the universe. Which is remarkable. When I found this, I was like, oh my God, it really is holographic. It really is that all the information of all the other protons in the universe are inside one proton. So of course that makes the proton a black hole. If you consider the vacuum fluctuation. But even if you take the universe, right? Let's say this is the universe. So remember, it has a radius of 10 to the 28 centimeter, right? If I take a bubble the size of the universe and I put 10 to the 55 grams of matter in it, it obeys the Schwarzschild condition. It obeys the condition of a black hole. So we live inside a black hole. This is why it's black out there. The universe we live in is a huge bubble that obeys the condition of a black hole. And so imagine if I put that mass in a proton, of course the proton obeys the condition of a black hole, right? But then that started to make me think, wait, so then well, there's two things. One is I calculated, okay, if I have two protons, black hole, and they're orbiting each other, right? And they're orbiting each other, can I calculate the force between these two black holes? The gravitational force that would hold these black holes together between each other. And I did. And when I calculated that, it gave the exact, but not approximately, it gave the exact measured value for the strong force. The strong force is the force that holds the protons together. Okay? And it was just thrown in by modern physics. Because when we discovered protons were stuck together in the nuclei of an atom, we thought that's not possible. They're positively charged. They should repel each other. Right? Like two magnets that repel each other. So then they invented a force called the strong force, because it had to be super strong to push them together against their will, right? Against the electrostatic force. And then they never said where the energy comes from to produce that force. So it's like a complete free parameter. It's like a full-on fudge factor. Right? So if you're not going to say where the energy is required to produce that force, of course, you're going to miss that you're dealing with black holes. If you actually calculate that energy necessary to produce that force in the mass of the mass of the proton, you end up with black hole protons. You guys see what I'm saying? So, of course, the mainstream was very upset with me when I published this. I got so many tomatoes for that one, right? I mean, it was just awful. Like, what is he saying? Protons are black holes. He's insane. They said the same thing when I told them there was black holes in the middle of galaxies, right? Well, they had one good point, though. I had to somehow prove that although the proton has the mass of the universe in it, what we measure is not the mass of the universe when we measure the proton, right? We measure a very small mass. The proton has a mass of 10 to the minus 24 grams. So I was off by, like, you know, a significant amount of orders of magnitude, right? And, you know, I don't need 10 to the 55 grams to make the black hole proton. The proton only needs 10 to the 14 grams to be a black hole. And there's a very interesting relationship there, but I'm not going to go into it. It's called the large number hypothesis. And actually, you know, Paul Dirac, which was one of the best physicists ever, came really close to solving it exactly the way I solved it. But when he got close to it, he was in his 80s, and, you know, they told him he was insane and he was senile, right? So the large number hypothesis was completely ignored, and he was so close to solving this, so close to solving unification. And so I had to prove this. I published this, and basically what I published is like, hey, isn't it cool that if you make the protons black holes, you get the exact force that we observe between two protons? And you know, I basically was saying that's most likely not a coincidence, right? Because, I mean, it's exact. It's not just like approximately right, it's exact. So but then I had to figure out, why is it that, okay, so imagine the little proton, and imagine the mass of the universe is in there in terms of information. Okay? You know, so then that means a proton is somehow connected, like entangled with other protons, right? And so maybe the whole universe is entangled, right? So I started to think that way. So if the whole universe is entangled, well, why are we not knowing that the whole universe is entangled? Because so let me backtrack a little bit of information, history information. When we wrote we wrote quantum mechanics, this thing came out. This is actually, Einstein pointed this out, that the way the math was written, it would mean that particles could be entangled at a distance. Meaning, didn't matter how far they were from each other, if you budged this one, the other one would budge. That's what the math was saying. That Einstein actually published this, called it spooky action at a distance, and he was trying to debunk quantum mechanics and then they start to measure it in laboratory. Okay, meaning that if you hit a carbon atom with a photon with a laser, you can get photons to be emitted by the atom. If they came from the one atom, they go away from each other. If you wiggle this one will wiggle instantaneously. And it doesn't matter how far apart they are. They did this over kilometers. And even at the speed of light, the information from this particle wouldn't have time to come back to the other one by the time you measure it. And still, instantaneously, they are connected. You change the polarity of this one changed automatically. So it doesn't matter if they were across the universe, because it's not related to the speed of light. See what I'm saying? So we know that exists. But we think that some particles are entangled. Now we've been able to entangle large objects like diamonds. In laboratory, we can entangle diamonds so that you can hit this diamond over here in the laboratory with a laser, and the diamond that's on the other side of the laboratory acts like it's being hit by a laser. And but we think that there's particles that can be entangled, and there's particles that cannot. Right? So we don't think that all particles are entangled, or meaning we think that there's particles that are entangled, and then there's decoherency. That is, there's particles that are not entangled with anything. Right? You guys are following me? Yes. Okay. So why do we think that? Well, because we tend to think inside a box and get stuck in it, right? So we say not all particles are entangled only because in the case in which they're entangled, we have access to both ends of the entanglement. So when we wiggle this one, we see this one wiggle. But what tells you that this particle on the end of my finger is not entangled with a particle on the other side of the universe? So when I wiggle this one, I don't see the other one wiggle. But it's still entangled. Right? It's just a question of my box, my perception, that I think it's not entangled. Do you guys see what I'm saying? Yes. So of course, it could be entangled. And so I start to think that way. So then I start to think, okay, if the whole thing is one, because like literally this equation said mathematically the whole universe is one. And it was nice because it's like, wow, you know, this has been in philosophy, and you know, many masters have come and told us the whole thing is one, it's all connected and all this. And it's nice when you know, in philosophy, but actually this was like the mathematical proof that this is really the case. Right? The whole thing is connected. Now remember, you're made out of protons, right? Right. So don't forget that part. Okay? Okay. So then the whole thing, so then I start to think, okay, well maybe the mass that we see when we look at one proton is the result of all the other protons acting on one. Like basically I was trying to find an equation that would describe what is the influence of all the information of the rest of the universe on one proton. You see? It would, like the exchange, right? And so I thought, oh, and so man, is that insane or what, right? Like I would go around, I'd be talking to my colleagues, physicists, and they'd be like, yeah, so this is what I'm looking for. Maybe you can help me. So we got to figure out a way to write an equation in which all the influence of all the universe on one proton, and it should give its proper mass by the time we're done. And they'd be looking at me like, yeah, good luck with that. You know? And so it took me 5 years. It took me, you know, from approximately 2000, from approximately 2005 to approximately 2010. You know, I was like day and night, you know. I was thinking about this, how can I solve this for all this time? And I went through insane amount of complex physics to try to solve it. And then when I solved it, is so fucking simple and so obvious. I can't believe I missed it for so long, right? It just blew my mind because I came like I'm writing really complex stuff, and then then it's getting simpler and simpler, and then it's like, oh my God, really? And so let me explain it to you, because like a 10-year-old can understand it. So basically what I did is I took a black hole that's well known. It's called Cygnus X1. It was one of the first ones that was found. And I basically said, okay, well, so let's think about this. I mean, this is not how it happened, but this is what it told me. Meaning, it's not how I solved the math, but that's where it landed me. Okay? I was trying to figure out, so let's think about it this way. So you got all the information inside a bubble, but only the amount of information that's on the surface is available to me from the outside to measure. Right? Because everything else is inside the black hole. So I don't have access to it. I'm only measuring a very small portion of the information that's able to come out. Right? That's on the surface. So I start to think, okay, maybe I should calculate how many Planck. So if each Planck is a little bit of information, or you can think of it as one Planck being the end of a Planck wormhole that connects to that surface, right? So then I should count how many of those there is on there. So I did that. I counted how many are on the surface, and that's 10 to the 79. So that's a lot on the surface of Cygnus X1. And then I counted how many are on the inside. Right? And there's 10 to the 118, which is a lot, right, on the inside of Cygnus X1. And then I thought, okay, well, the way the math worked out, it starts to reduce, and I start to think, okay, here, then there must be some kind of like, maybe it's just a relationship between the amount that's inside to the amount that's on the surface, like a pressure, right? Of what can be expressed. Only a small portion can be expressed outside. So then I made the ratio, right, of the inside over the surface. And I multiplied it by 10 to the minus 5 gram, which is the mass of one Planck. So basically I wanted to know the energy of the ratio, the energy of the ratio of information in the volume to surface ratio of energy. And when I solved that, it gives the exact mass of the black hole. Right? Exactly, which is what I call a holographic mass solution, give the exact solution for the Schwarzschild solution to Einstein field equation. So I solved Einstein's equation for gravity, but using Planck quantum bits. So now you start to see the bridge starting to connect between relativity and quantum physics, right? I'm using quantum physics to solve gravitational equations. So yeah, go ahead. To information? Well, in information theory, energy is information, or information is energy. You can think of the position of any particle in the universe relative to all the other particles represent an energy event, right? Like a particle moving through space. It really was describing quantum gravity at the cosmological level. And you know, this is so simple. Right away, I called my colleagues and asked if this was known. You know, I thought, oh, this has got to be known, right? Everybody knows this, right? Because it's like, wow, it's like a 10-year-old, this 10-year-old algebra, right? And so I'm calling around, and they're like, really? It comes out right? I'm like, yeah. And it's like, no, yeah. And it's like, they're calculating, holy shit, you know? And so, yeah, it was unknown. It was missed. It was missed. And one of the reasons it was missed is because what I didn't tell you here is that I made the little Planck. I made the little Planck a little spherical black hole, right? I took the Planck length, and so the Planck length usually is L, script L, and I divided it by 2, right? Because the L would be the diameter, divided by 2 would be the radius, and I made a little sphere. I made a little spherical Planck entity. And that's what I tiled when I calculated, right? This is not two-dimensional. That's just the equator of the little Plancks that I'm showing on there. But they're little spheres. And all the people before that were, it's called holographic theory, were doing, instead, they were tiling L square. Right? Because everybody works in math and don't necessarily think about the geometry. So they go, oh, L square will tile the surface. As if the universe was making like square pixels of two-dimensional size. This is why, I don't know if you've seen in like Popular Magazine on the cover, are we living in a holographic universe? Right, that's because of the holographic solution that was given, which is similar to this, that was the result of trying to solve the black hole information paradox. And Sutskin said, well, the information doesn't disappear when it falls into a black hole. It's tiled on the surface holographically. And then they calculated, it's called the holographic principle. It is in the mainstream. And they calculated the amount of Plancks that would tile on the surface of the black hole, and it gives the right energy, the right temperature for the black hole. But not its mass, right? Just the temperature of the black hole. So, but they were tiling L square. So and this is why, if you read these articles, it says, is the universe a 3D representation of a 2D holographic surface? Okay, I'm mentioning this because it's important you know. The universe is not two-dimensional. Dude, really? Two-dimensionality does not exist. It's not, it's like a thing in a human's mind. It's a model of mathematics. This is when, like, they make a model and then they forgot they made a model. And then they think it's really like that out there. It's like, it's not. There is no surface anywhere in the universe that has no thickness. If it's there, it has thickness. Even if it's just 1 Planck thick, it's still 1 Planck thick. I mean, in 1997, I was coming back from a conference in a plane with one of the most famous mathematician topologists. He wrote the book on topology, right? And so he's, you know, on the window side, and I'm on the aisle side. And so he's got 37,000 feet on one side and me. So he can't go anywhere for 6 hours, right? So I'm just bombarding him, right? He's just hating it, right? And I'm like, so what is the dimensionality of a sphere? And his answer, two-dimensional, right? Because that is what they do in topology. A sphere is a two-dimensional object. And I'm like, so, because he says it's a surface. I'm like, okay, so let me help you with this. I pulled out a piece of paper out of my suitcase. I said, make me a sphere. Right? He's like, well, I can make a cylinder and then cut the top and, you know, kind of squish it. I'm like, yeah, well, that won't be a sphere. And they're like, no, but I could cut it more. And they're like, okay, how much more do you need to cut it before it's a perfect sphere? Well, a perfect sphere would take an infinite amount of cuts, right? You'll never get there, right? A sphere is not a two-dimensional object. A sphere is a constituent of smaller spheres, right? That is a constituent of smaller sphere, which is it is nothing that's two-dimensional. When you write on a piece of paper, you know, a smiley face, right? You're not, like, you can say this is a two-dimensional face. But that's in your mind, right? Because the ink that's on the paper, it's got thickness. If I shrunk myself to the microscopic level, that'd be a mountain, right? And then, like, the thickness of the paper, I can put calipers on it. It's got thickness. There's nothing two-dimensional about it. Except your mind that made it two-dimensional, right? So, of course, the universe is not a two-dimensional, like a three-dimensional holographic projection of a two-dimensional surface. Of course not, right? So when I wrote this equation, I made the little Plancks little spheres, and then I calculated. And that's why my math went sideways for so long. That's why it took me so, because I kept on not understanding until I got back to fundamental geometry. Because if you did this with L squared, then it doesn't add up at all. You're off by orders of magnitude. You would never find it, right? So then I thought, okay, well, I've got quantum gravity. If it's working, then it should work at the quantum level. So I took the proton. I did the same thing. That's the surface. And that's the inside. And notice, you know, there's 10 to the 60th protons, Plancks inside. 10 to the 60th multiplied by 10 to the minus 5 will give you 10 to the 55, which is the mass of the universe. And there's 10 to the 40th on the surface, which is still a lot. And then, so imagine you're writing an equation that has the mass of the universe in it. And you're hoping by the time you're done with the equation that it outputs the correct mass of one proton in that universe, right? So even if you got close, you would think, wow, you know, that's kind of cool. So I was hoping I would be at least within like 1 or 2 orders of magnitude from the mass of the proton, and that would, like, I'd be happy with that, right? But when I calculated it, it gave me the mass of the proton within 0.0012 of the measured mass in the laboratory. So I was like so amazed. I was like blown away, right? Huge numbers giving exact or very close to exact result for the proton mass. You know, that was just mind-blowing. So I was on a cloud for like, I mean, that has been 5 years I'm looking for this, 30 years of research behind it. I'm like walking on a cloud, right? I'm like, for like 2 weeks, I'm not touching the ground. All the people at the lab, you know, they're like, yeah, I don't know, Nassim. We were like on 13 acres, and I'm like walking around the 13 acres with my notepad constantly recalculating to make sure I didn't screw up somewhere and put the mass, the proton in my equation somehow, and then it comes back out. Of course, that would be circular, right? So I'm trying to break it. I'm thinking it can't be that simple. I must have screwed up, right? Okay. And so like I'm hitting myself with the pad. So you can imagine, my staff is like, I think we're losing him. So you know, I can't break it. I'm like, okay, this is it. And I'm getting like crazy chills, and I'm integrating inside my own body because I'm thinking, now I'm like seeing like the wormhole network, because you see there's 10 to the 40th wormhole attachment on the proton, and then you can imagine, and now, you know, Montesina and Sutskin and others are starting to realize that entanglement is the result of micro wormhole, Planck wormhole that connects particles. See, they're coming to that conclusion completely independently, right? So, but I'm visualizing this. You can imagine my head is like, whoa, I'm seeing all the wormholes of every proton connecting to the whole thing. And we know that there's approximately 10 to the 80th proton in the universe. So I'm thinking, why is there only 10 to the 40th connection to one proton if it's all connected? Then I start to see, oh my God, one proton is connected to 10 to the 40th, and the 10 to the 40th are connected to 10 to the 40th. And that's how you get to 10 to the 80th, right? Which 10 to the 40th is much smaller. It's not half of 10 to the 80th. Remember, like these are exponent, right? So 10 to the 40th is a very small number compared to 10 to the 80th. Anyway, so they all connected. So you can see now, I could see the fractal network, you know, working together. And the information transfer. And of course, if a proton is connected to this proton, to this proton, to this proton, to this proton, like all the way to over there, we would never know, right? Because we're not measuring the two. So there's so much influence of all protons to each other that we don't see the entanglement. We only see, we call it mass, the energy or the information going through the event horizon. The bits coming in and out. We call it mass. We call it energy.